general relativity, step by step. We've got this beautiful Friedmann equation here, and I made the observation that because rho was a function of time, we couldn't solve this equation directly, and we needed equations of state to close it. The equations of state I'm going to use are developed in cosmology step by step, numbers 26 through to 30. And what we saw there is we had two equations of state, one for matter, which is this term here, and one for radiation. So I'll do the matter one first. What did that say? That said that d by dt of rho matter, I'll just use an m. A cubed plus pressure term d of a cubed by dt equals 0. Yeah, and that was basically a statement of the first law, although it had to be significantly modified, or we had to do a lot of work to make sure that that equation was actually true in the co-moving coordinate system that we're considering. What I'm going to do is I'm going to assume that the pressure equals 0 on the grounds that the galaxies move slowly. Slowly compared to the speed of light, of course. It's tempting when you look at the galaxies or the clusters of galaxies to say, well, they don't bounce off each other, but and therefore the pressure must be 0. But that's not the case. You can have very high pressure gas, which is made out of molecules which are moving very, very quickly, but they're very, very far apart. So the mean free path is not really the relevant parameter here. The relevant parameter is that the galaxies move slowly in our co-moving coordinates. It's not helpful to look at a distant quasar and say, my goodness me, that's moving really, really quickly. That speed isn't interesting. It's the speed in the co-moving coordinates. You've got to go to that quasar, you've got to build an elevator around the damn thing, and then you've got to say, the velocities round about here are small compared to the speed of light. And therefore, that is justifying our assumption that the pressure equals 0, which means that I can ignore this term here. So what that says there now is that d by dt of rho m a cubed equals 0. So that tells me that rho m times a cubed equals a constant equals density m for matter. Now, whatever this thing is now, it's going to be the same for all time. A now cubed. And of course, what I'm going to do is I'm going to take this value here and I'm going to substitute it into my Friedmann equation here. What's the other term that we had? We also had an equation of state for radiation, and that was slightly different, radiation being sort of the ultimate relativistic gas, I guess. And what we found there was that rho rad, I'll just say R for radiation, times a to the power 4 equals a constant equals what? That's rho radiation now times a now to the power 4. It's always worth pondering. Just make this observation that there's a cubed there and a 4th power here for radiation. It just goes to show how important the distinction between relativistic and non-relativistic fluids is. It's a whole difference, a whole single difference in the power that we use. Okay, so I'm going to substitute these things back into my Friedmann equation. What does that look like? Well, we have a dot squared minus 8 pi g over 3. That 3 turns out to be quite important. Times, and then what we had before was rho m plus rho r plus rho v for vacuum, times, I think there was an a squared there, equals k. Okay, so I'm just going to substitute, well, we'll do this one first. This rho r is equal to, from this formula here, plus rho r now, a now to the power 4. That's just looking awfully fiddly, isn't it? It's just a constant. some constant, over a to the power 4, and this one of course was some other constant over a cubed. I'll rewrite that sign there, plus. Okay, so this tells us that these three terms change at different rates, at different epochs in the universe, and we can use that fact to help us solve them, because we're going to consider different times of the universe or different epochs in the universe's history in which one or other of these terms dominates the other two, and that makes our mathematics a lot easier. So I'm going to stop there. Stop.